Hey class, we're just finishing up our notes for section 6.1 where we were finding the area between curves, and we left off, we had just finished example 4, I believe, where we were finding the area between these two curves, where we had a cubic and a quadratic, and we had to write two different integrals because they changed positions. First it was the cubic on top, and then it was the parabola, the quadratic, that was on top. So we had to write two different ones, and then total the areas of each. In this example, the thing that's a little different about example 5, it says horizontal representative rectangles. And what that means, now all these other ones, I didn't talk too much about the representative rectangles, but what they mean by that is, really it's the distance between the two curves, and when we subtract the top minus bottom, as we were saying, f of x minus g of x, that's giving us that distance. And really what we have then, when we talk about integrals, we're summing the area of all these infinitely thin rectangles. Well, these ones are vertical, and the reason that they're going to be that way is because the function is explicitly written, a function y in terms of x, or f of x in terms of x. And so when they're written in that form, then we're going to have our function values are y values, making our rectangles, representative rectangles, vertical. Now in this case, and granted, we could solve the linear one quite easily and put it in terms of x and solved for y. The quadratic would be, we still could do it, but we'd have to deal with a plus and minus square root situation, and that's going to make it a little more difficult for integrating. So because this one is x equals 3 minus y squared, it is a quadratic, but if you recall from working with conic sections, when it's written in this form, it's going to be a parabola that's opening to the left. And if you're not totally sure, just make an XY table, okay? And so when it's in this form, we're going to pick input values for y and then calculate x values. So I picked 0, 1, and 2 to input in for y, giving me x values. So if I put in a 0, I get 3 for x. If I put in a 1 here, I'm going to get 3 minus 1, so I get 2. And if I put in a 2, 3 minus 4 gives me negative 1. So then I've got these ordered pairs that I graphed. So 3, 0, which turned out to be the vertex, and then I've got 2, 1, and I've got negative 1, 2, giving me that branch. Now I could have maybe picked some other values and put them in here as well. Like I could have done negative, possibly. Well, what we see then, actually I guess what we're seeing here too, if I were putting in, let's say, a different y value, like the opposite sign, negative 1 and negative 2. So if I put negative 1 for y, and I'm going to get the same output for x because I'm squaring that, so I get that 2. So you can see that symmetry happening, and so if I put in a negative 2, I would get negative 1 again, and so on. So these would be the points that would show up, giving us that symmetry, in this case horizontal axis of symmetry. Okay, and then my other equation is just linear, and for graphing purposes I just changed that around and solved it for y, so I could see my y-intercept was negative 1 and that my slope is 1, and I just graphed that. And then I can see my intersection points to be at 2, 1, and at negative 1, negative 2. So I've got those x values that'll help me with my bounds as I set this up. Now again, it talked about horizontal representative rectangles. So the distance between these curves is going to be represented this way. And because they're written that way, again, it has to do with the fact that these are functions that are written as in terms of y. They're solved for x in terms of y, and that's why we're looking at a little different representation here. So instead of thinking top function minus bottom function, when it's in terms of x, we're thinking the right, the larger function is the one on the right, since our function values are x values now, and we're minusing the left function. So the right function here is going to be the parabola, the left function is going to be the line. And so that's what I'm doing here. So 3 minus y squared minus, and then I've got y plus 1 as my linear. So when I combine those terms together, the like terms together, negative y squared minus y, and then if I'm subtracting that 1 from the 3, I get plus 2. And again, like we said, our bounds are going to be negative 1 to 2 because those are the x coordinates of our intersection points here, okay? And so we just go through and integrate that, and simple power rule, negative y cubed over 3 minus y squared over 2 plus 2y, and then I'm inputting the 1, and it gives me negative 1/3 minus 1/2 plus 2, and then I'm subtracting, and I'm inputting my negative 2, giving me these values here, and as I simplify that and combine and come up with my solution there, I get 4.5 or 9/2. Okay, but the main difference on this is the fact that we have horizontal representative rectangles because the functions are written as x equals something in terms of y for each of these. And when that's the case, then you go with the right function minus the left function as you set up your integral. Okay, so that's the main difference there. And I believe there is one on the quiz that's kind of set up in this way. All right. The last example, I'll show you how it's set up. It's pretty tedious, and it's definitely not the easiest way to find the area of a triangle that's on a coordinate plane. There's other methods for doing that with matrices and some other methods from algebra, but it is possible to do this one using our integrals, but again, like I said, it's going to be kind of tedious because all that they gave us were some ordered pairs, which were the vertices of the corners of the triangle. So I graphed those out, and through, knowing that we have 2 points which make a line, we can determine the equations of each of these lines, just counting out the slope and then using a point and coming up with an equation. So I wrote those out. So this line over here would have been the equation 2x plus 10 at a slope of 2 and a y-intercept of 10 if I continued through there. This one, and again, it came to fractions, and I would have had to use like point slope form, figure out the slope. I counted it out to be negative 11/5. I was down 11 over 5, and then plugging that in along with one of the ordered pairs that was the end point, I came up with the y-intercept of 29/5. So it's kind of an ugly looking line. This one over here was y equals negative 1x plus 1. Now, if we're going to apply our top minus bottom, because I did write these explicitly y in terms of x, so we could do vertical representative rectangles, but for part of it, we've got this line 2x plus 10 above the line y equals negative x plus 1, and then it switches to a different line continuing being above the y equals negative x plus 1. So I did it in two parts. So it was the integral of 2x plus 10 minus negative x plus 1, which is what I have here, and the x values for that would have gone from negative 3 to 1, because I'm starting at negative 3 and then going to, negative 1 right there. So I set up that integral, and then the other one is going to be, my top function is this line, negative 11/5 x plus 29/5, minus, again, the bottom line is still the same equation, negative x plus 1. Doing some simplifying here and here, we came up with 3x plus 9, and this one is negative 6/5 x plus 24/5. Again, you just got to go through the arithmetic and combine your like terms. Here now we're integrating, so 3x squared over 2, this is just going to be 9x, evaluating it from negative 3 to 1, and that comes out to 6. And here again integrating, if you add a power of 2, x squared, and then dividing by 2 would actually give you negative 6/10, reducing down to negative 3/5 x squared. This one 24/5 x, evaluating it from negative 1 to 4, because that's where our x coordinate ends over here is at 4. And just plugging those in and doing the arithmetic gives you 15. Total area comes then to 21. So this triangle was an area of 6, and this one was a 15. So again, I don't think you'd ever be asked to do one like that necessarily on an AP exam, but it's just another example of how this this property of area between curves, and these were straight lines, so probably a different, more efficient geometric way of doing that than this method, but it does work. So that's all we have for area between curves notes, and we'll continue on with using this information to find now volumes of solids with revolutions around an axis, and then also with cross sections.